Hi, this is Professor Dorr, and this is lecture 14A of EE310. In this lecture, we're going to do impedance matching with an ideal transformer. So what is impedance matching? Because you've heard me say that impedance matching and power factor correction and maximum power transfer are just all the same thing. And I want to make sure you think of them this way, because then it'll make them all easy for you. So what impedance matching is given a Thevenin source, like this right here, given a Thevenin source and a load, design a lossless network, meaning no resistances, to go between them so that I get maximum power transfer out of this source. Or in other words, I'm stuck with a load. I'm stuck with a source. Design the thing to go between them that will not consume any power, but will get maximum power transfer out of your source. So it's really a very cool thing. If you found this lecture searching for RF matching, this is the same problem, but we're not using L networks or anything like that. We're using a transformer to do the matching here. So let's get started. So we're given this source, and I can see that I'm given the frequency, which is going to be important because I'm going to need to know the impedance of this inductor. I'm given this source and this load, and here are the rules. I'm going to use an ideal transformer and one additional component so that the load receives maximum power from the source. And I'm narrowing things down by saying the additional component has to be placed in series with the 9 ohm source resistance. And the reason I do that is because you could also do it by putting the component on the secondary side. But when I assign this, I want all the solutions to look somewhat the same so it doesn't drive my grader crazy. So I said you got to put it on this side. And the additional component has to be a capacitor or an inductor. So you notice that one of our components is the transformer. That's lossless. The other component is either going to be an inductor or capacitor. That's lossless. So we're doing the right kind of stuff. So what I want to know is the component value and the turns ratio. Let's use the concepts to just get us a little piece of information. For maximum power transfer, I know that I want a conjugate match, right? So if this looks inductive, in order to get a conjugate match, or in other words, this is plus J something, I'm going to need a minus J something over here. And the transformer, when it reflects the impedance, it does it just by a scalar. So this plus J is still going to be a plus J when it gets over on the other side of our transformer. So that means I'm going to need a minus J over here, which means my component is going to be a capacitor. So here's the circuit. We've got our Thevenin source with its 9 ohm series resistance. And I'm going to draw my dotted line here because that's kind of where my Thevenin source boundary is. Here's the new component I'm going to add. We kind of already figured out it's going to be a capacitor. Here's my transformer, and here are the two components that we need to match here. So here is the circuit that I'm trying to design, and I need to figure out what the turns ratio is, and I need to find Z new. So here's our strategy. What we're going to do is we're going to compute the turns ratio to match this 9 ohms. Or in other words, we're going to come up with a turns ratio that makes it so that our 180 ohms here gets reflected into the primary as 9 ohms. So that's the first part of our maximum power transfer, because our resistive parts will be the same. Then we'll pick Z nu so that it is the complex conjugate of whatever this inductor ends up being. So let's do it. You went out? Okay. Sorry, that's Bella. All right, so we have our 10th Henry inductor here. Let's figure out what its impedance is. It's going to be J 2 pi FL, or J omega L. Look at that, I forgot a J there. Put the J in. Or J 2 pi times 300 times 0.1. And I get J 188.5 ohms right here. And you can see I kind of did some housekeeping here. I said, I'm going to call this Z, and see my little 90-degree arrow there? That says that is Z in looking in at the primary. And here I have my dotted line for my Thevenin source, and I'm saying Z load is on the right side of my dotted line. So that's just going to kind of help me keep things straight. Okay, go out. That is Bella. Okay, so the first thing I'm going to do is I'm going to take my load and I'm going to reflect it to the primary side. And I'll use my equation Z in equals ZL, which is actually out here. So Z in is going to be all this stuff divided by n squared, right? So I take my 180 plus J 188.5, divide it by n squared, and that's what I'm going to see right here. And when I do that, I'm going to set my turns ratio n so that the real part of Z in is going to give me 9 ohms. It's going to match that real 9 ohms that I have here. So what I do is I'm going to say that 180 divided by n squared, or this resistor divided by n squared, has to reflect to 9 ohms. Here's that set in an equation, and I get n equals 4.47. So I just set the turns ratio of my transformer. And so now Z in, looking in right here, is going to be 180 plus J 188.5 divided by the turns ratio squared, or 9 plus J 9.43. Let's draw that in right here. Let's replace Z in with what we know it is. Here it is right here. See, I've got my 9, my Z nu, 9, Z nu, and then my reflected impedance. And I'm digging what I'm seeing because I've got my 9 right here. So as far as getting a conjugate match to this source, I'm on the right path because I've got the resistive part handled. So now, for maximum power transfer, I need this load here to be the conjugate of Z Thevenin. And so Z Thevenin is going to be just 9 ohms. So that means I want my load out here to be 9 ohms. But I reflected J 9.43. Well, capacitor to the rescue, because the capacitor is going to give us a minus J in series with that. So in order to make everything to the right of the dotted line look like just 9 ohms, I need to put something here that is minus J 9.43, or Z nu equals minus J 9.43 ohms. So it's got to be a capacitor. We figured that out way up at the top, but It's got to be a capacitor because Z is a minus J. So what I'll do is say my capacitor is minus J 9.43, which equals 1 over J omega C. Here's my J, here's my omega, here's my C. Let's calculate C, and I get 56.25 microfarads. So here's my resulting circuit. Here's Z new, here's my transformer. And this load out here is going to receive maximum power transfer from this source. And it does it without wasting any power. And that's just one of the cool things that transformers can do for you. As always, look forward to seeing you in the next lecture. Look forward to seeing all my students in office hour.